All right, so next I will talk to you about this AVR microcontroller. So we have been using one of the AVR microcontrollers in our labs so far, and that's the processor on the Arduino board. There are different kinds of AVR processors on different kinds of Arduino board, but many of them share the same architecture, especially instruction set. Although the exact number of registers might be different. The memory map might be a little bit different. But let's go through some of the important concepts in these microcontrollers. And in these set of slides, we'll look into the details of these internals of these microcontrollers and show you some examples using assembly language to operate these, to program these microcontrollers. And today I want to talk about the I/O part, and in later classes we'll look at the timer and interrupt in these microcontrollers. Okay, so this is the system architecture. There are several things that you should look into. Well, first of all, this AVR CPU, this is the center of this microcontroller, because without it, the processor cannot be programmed, cannot do the computation or any processing task you want it to do. And then we have program memory and data memory. As we show in this diagram, the program memory and data memory are in separate spaces. So we show one on the left, the other one on the right. What really mean here is that this is a separate program memory from the data memory. And this is what we call the Harvard architecture, where the memory spaces used to store programs are different from the memory space used to store data. That means you will find the programs and data in different set of memory, and physically they're in different places. And also when you try to find them using addresses, they are accessed differently. Now, this type of design is different from processors like Intel's x86, Xeon, or Core i5, 7, all these processors. In these general purpose processors, they use so-called von Neumann architecture. In this case, the program and data are in the same memory space. So if I draw a diagram, you'll see that this is the Intel's i7 microprocessor, and you have one box, that's the memory, which stores both program and data. So that's a major difference between Harvard architecture and versus the von Neumann architecture. Again, this AVR use Harvard architecture. Like many microcontrollers, for example, from the microchip, PIC microcontroller use also Harvard architecture, where the program memory and data memory are separate. So between the CPU and these memory, of course, we fetch instructions from program memory. So all the software, you wrote your programs for lab 1, lab 2, and later for lab 3, after compilation, all the instructions are going to be stored in this flash. And in contrast, data memory are based on SRAM. SRAM is called volatile memory, and flash is called non-volatile. Volatile versus non-volatile depends on whether the memory component retain information after power off or not. So flash can return information after you power off this chip or power off the system. Whereas for the SRAM, it loses all the data, all the information when you power off this chip. And because we have instructions are stored in the flash, so you don't have to program again. You can just plug it back into a USB cable, your program will run. You don't have to open up the Arduino IDE and then run a compilation, run the programming process again. And that's the benefit of using this flash type of memory. And next thing we want to look at is the I/O ports. So the I/O ports are the, sorry, it's the wrong button. Are the ways for the microprocessor to interface with the outside world. All the things you do with your buttons, with your LED, with the joystick and the accelerometer, all these sensors are through these ports. Not necessary to this one, but you'll go through some of the ports. And the way to program these ports for read or write is through this I/O data bus. And you can send the data out through this I/O port if you set the port as output, or you can read data in through this I/O port if you set this port as an input port. And so that's bidirectional. And we'll see shortly how we set the direction so that we can use the port according to our needs. TC012 are the timers that we will talk about in future classes. Those are the interesting units that you can use to set up specific tasks on a preset schedule. You'll be able to generate interrupts to allow you perform a predefined task at certain time intervals. Also, there's possibility of doing external interrupt. ADC is for analog to digital conversion. And you have 8 analog inputs, and you can use AREF, this pin, as the reference voltage. Then you can perform analog to digital conversion using this ADC component that's built in onto this chip. USART, or sometimes called UART, UART, this is the serial interface. So for the data transfer through the RS-232 protocol, you're going to be using these ports, one for input, one for output. Let's take a closer look at the I/O ports. This ATmega 328P has 23 GPIO pins that are grouped into 3 I/O ports, and they are color-coded on this diagram. Port B refers to the pins PB indexed from 7 to 0, so you have 8-bit bidirectional I/O pins, and they are colored in this type of green. And then similarly, port C has a few pins from 6 to 0. It's colored in this light blue. And then port D, 8-bit bidirectional I/O, and colored in purple. Each pin can be used individually for input to sense an external signal, or be set as an output so that you can drive a signal into the external world. So the things you do using buttons, using LED, are all made possible by using these ports. And you may recall the instructions or statements you use in your program, C program, how to set that port to be an input and output, and how to read or write through that I/O pin, through that port. And we're going to see shortly how we do that using assembly language program. So once you have this chip, and this chip is put onto an Arduino board, and this is the one that I used from last class, this Arduino Uno board. The individual pins are routed to these connectors. And the numbers do not match exactly, but this diagram shows how these different ports mapped to the pin numbers on the socket, so on these two sockets. And some are labeled as analog, for example, from A0 to A5, and these other ones are marked as digital. There are 14 digital pins numbered from 0 to 13. They can be used for digital input or output. And pin 0 and 1 are also connected to the USB port. There are 6 analog pins labeled as A0 to A5, but in fact they map to port C from PC0 to PC5. And those are analog input signals. So from this map, you can see that from the processor point of view, it names or it assigns the pins as PB1, PB2, all these port names. And these pins can eventually be connected or routed to these connectors, and you can label them using different numbers. For the Atmega 2560, it's a larger board and uses a different processor, still from the same AVR family, but the pin numbers will be different and the connector numbers will be also different. But the way to use them are very similar. So they have pins grouped in ports for either analog or digital purpose, and then you can configure them, you can connect them individually. AVR has 3 8-bit registers to access the pins of a port. And for each port, you'll find such 3 registers. DDR is data direction register. It configures the bidirectional pins for input or output. If you set a 0, that means an input. If you set to 1, that means that particular pin is the output. Now note that these 0 ones for input or output can be different from processor to processor or from microcontroller to microcontroller. For example, in PIC microcontrollers, they use 1 for input, 0 for output, which I think is more intuitive because 1, that's a I, and 0, that's a O. But you want to just make sure that you understand clearly what value represents input, what value represents output. The second register is the port register. It refers to port data. It stores the bits driven to the external world if the pin direction is configured for output. On the other hand, we have a port input register, or PIN. This is for reading values as the digital inputs from the external. So you store the digital external pin voltages, and it's read if the pin direction is configured for input. So for example, we have a port B. For this port B, we have the corresponding 3 registers. So we have DDR B, port B, and pin B. And we have these 8 bits in each of these registers. And for bit n controls pin and bit PBN. So for example, if I focus on bit 0, so this DDR B0, this value here will determine for PB0 pin, am I setting it as an input or output? So if the value here on this bit is a 0, am I setting this PB0 as an input or output?
It would be input.
Yeah, so it's an input because 0 indicates that I would like to use this particular bit, and that is 0, so PB0, as a input. That also means we actually do not use port B0 anymore, because port B0 is for outputting the data. So we're going to be using PIN B0. This is the input register. So I set 0 on DDR B0, then I'm going to read the actual input value from this bit 0 of this PIN B register. So if I read a 0 here, does that mean I have a high voltage VDD or a 0 volt? If I read a 0 from this bit, what will be the voltage that's connected to that PB0 pin?
0 volts?
Yeah, that will be a 0 volt, because that value that I read indicates the external value applied to that pin. Now, if I make a different case, let's say I set DDR B0 as 1. That means I want to use this PB0 pin as an output pin. I'm going to send value out through this pin. And then I will use port B0 rather than the PIN B0, because this is for input. I'm going to using this one as the way to send out a value through this PB0 pin. So if I set 1 here, okay, in this case, I have 1 here to indicate it's output, and I have a 1 here in this on this 0 bit. What will be the voltage that you can observe on PB0 pin? Or in other words, way, if I connect the anode of a LED to this pin, will that LED be turned on? Well, the answer is yes, because if I set 1 on port B0, this is to say that I want to drive a VDD on that port, on that pin. So if I connect the anode of LED, and that LED will be turned on. Okay, so this is how we use 3 registers for each port to control the direction of the transfer, and also set up the output value or read the input value from the registers. And this is a very typical pattern that people use to in different microcontrollers. In PIC pick command controller, they have exactly the same design. Just the names of these registers are a little bit different, but they also have this direction register to control the direction, and one register for output, the other register for input. So it's important that you understand this. Okay, next thing is about the data memory map. SRAM is treated as a part of the larger data memory address space. The data memory map defines the data addresses of all storage elements. Again, note here that program memory is separate. It follows the Harvard architecture. So the program memory and data memory are in two separate memory spaces. So all things you see here are not related to program instructions at all. What we have here is the data memory. We have 32 general purpose registers. Each of them is 8-bit. And we have 64 I/O registers. And we have 160 external I/O registers mapped in this space. And then we have the internal SRAM, 2 kilobytes. So what you see on the left side is so-called the load store address. Load store address are from 0 to all the way 8FF. So if you use load or store instructions like this one, load or store instructions, these instructions will assume that you are talking about these addresses. And you can access any of these information using these addresses, and provided that they are mapped properly to these different spaces. So you can load any values from the general purpose registers or store the value into the registers using addresses from 0 to 1F. Or you can say I want to store something at address 104 in hexadecimal, and that will put the value here. So the load store address will assume that you are talking about this address space. And in different parts of the memory space, it's mapped to different things. Between these space, it's mapped to an SRAM. Between these things, it's mapped to general purpose registers. And between 20 and 5F, these are mapped to the 64 I/O registers. And also, there's some other registers reserved in this range. For 64 I/O registers here, these registers not only have these load store addresses, they also have I/O addresses. You can use I/O instructions to access these I/O registers. But in that case, you need to use this this address range from 0 to 3F. If you use 3F as part of your I/O instruction, using in or out to access these addresses, let's say 3F is the address you access. That's the same as you use 5F with this load store instruction. And when you use 5F, those are treated as memory address. So they are going to be mapped to this location. And that's the same as the 3F when you use I/O address. So this is, a very interesting example that shows you the address space, the addresses, and how that relate to instructions. You should not treat these numbers literally, because these memory ranges could be different processor. But the idea of mapping one resource, this being the case, I/O registers, to either load store address or I/O address, this is interesting to know and also to understand the possible ways to access the same resource. So I recommend that you take a look at this closely, understand it. So earlier we talked about the registers for a particular port. We used the example for port B. So we have the data transfer direction. We have the PIN for input and port B for output. These registers corresponding to port B, they are I/O registers. And they are mapped to 03 for this case, for this particular register in the I/O address space, and then 04 for DDR-B and 05 for port B. So if I go back to the previous diagram, so we are talking about registers here for that address, 03, 04, and 05. So that's somewhere here. Okay. Now you can use I/O instructions to access them, but if you want to use load store instructions to access them as memory locations, you can do that. But in that case, you need to add this 20 because it's 20 corresponding to the 0. And so 21 corresponding to 01 and 23 corresponding to 03. And that 03 is PINB and 04 is this DDR-B. So that's why we have this simple translation formula. The load store address equals the I/O address plus 20. The following few lines shows you the how you can program the pins. Like we said earlier, let's say you want N as the pin index. N could be 0 or 2 through to 7. In the pin configuration, you can set bit N to 0 if you want to use that pin for input, or set it to 1 if you want to use it for output. If you read pin, if you set it as an input, you will read the PIN register. And in our case, we're going to be reading PINB, read 1 byte, and then mask bit position N. Because when you read from this register, you are reading 8 bits from it, and you only use one of the bit at location N, so you want to get rid of other bits to mask other bits out, or just retain this only bit in position N. For writing, or for output, you can write the output bit value to bit N of the port register. In our example, we'll write that to port B. So you can set your output voltage on that particular pin to be 0 or VDD. Okay, so let's put them into action. We have a very simple design. It's probably part of your lab 1. What we want to do here is we want to use one of the pins, that's pin 12 on the Arduino board, on the Uno board, to detect the push button position. So the push button could be closed, could be open. So that's what we want to detect. The circuit is very simple. We have the push button. One side is connected to the 5-volt VDD, and the other end is connected to the pin 12 on the connector. And also we have a current limiting resistor so that we don't short the circuit when we press the button. Now, pin 12 on the Arduino board is wired to pin PB4 of this microcontroller. So we're really talking about bit number 4 of port B. So all the things we do for this design, we should deal with PB4 for this operation. So first thing we need to do is to configure bit 4 in DDR-B so that that pin will be used as an input. And then once we have that configured, we can read the port register PI and B and extract the bit from it, and we only look at bit number 4 or index number 4. Okay, so that's what we're gonna have. If you write a C program like you did, you can use the Arduino libraries, built-in functions. But here we want to show you underneath what happened. So when your code set the pin mode, read the value from the port, underneath, this is what we'll have in terms of assembly language instructions. First of all, we will clear R1. R1 is one of the general purpose registers. We will just assign 0 to this register. And then the next instruction is an out instruction 0x04, so hexadecimal 4 in R1. Now we're using an out instruction. Out and in instructions are IO instructions. So when you use IO instructions, we use IO addresses. So let's go back quickly to see what is 04. When you have IO address 04, that refers to this register, DDR-B. So we're going to assign a value to this DDR-B, and the value is 0. So essentially, we put 0 to this DDR-B. DDR-B has 8 bits. So all the 8 bits are 0 now, including bit index number 4. And that did exactly what we want. We configured PB4 as an input because we now have a 0 on the bit 4 of DDR-B. The next instruction is to read value from PI and B. The reason we know we're reading from PI and B is because of this address, 03, and that's the IO address for that register. So we're going to read value from this PI and B and put the value into another general purpose register that's R16. And we can do this safely because we already configured the pin as a input, so we'll be able to read up to 8 bits to this register, including the value on bit number 4. Now the next instruction is the AND instruction. If you AND, so you're going to be doing a logic bitwise AND operation between R16 and this hexadecimal value 10. Hexadecimal value 10, that is, you have a 1 on bit number 4, and all the bits are zeros. So when you AND this, you basically mask out all the other bits except bit number 4. So up to this point, you will have the value on bit number 4 stored in the result, the register that's R16. The next thing you can do is to check the value. You can do a lot of different ways. You can shift the value to the very end, or you can just compare with the known value here. but essentially with these 4 instructions, you set the direction of the port, and then you're able to read the value from the input register, and then mask out the unnecessary or unused bit to just keep the value that you are interested. It's very simple. It's it just shows you exactly what happens when you have these set pin mode API calls, and you read the values in your C program. If you are interested, you can use a simulation tool, a debugger for AVR processors. You can download that from the Arduino from AVR website. Then try a few commands, but I won't go into that. Essentially, this shows you what's the actual content in those registers when you actually run this program. A few other assembly entry instructions related to bit operations. Set B A comma N is to set bit number N of the port register and address. So this will, you need to provide address like 03, 04 that we used earlier, and that's the IO address. And you can use this to set the bit number index N of that register. Set means assign 1 to that location, bit location N. And on the other hand, you can clear the bit. So CBI is to clear bit N of port register and IO address. And there are several instructions like this. Skip next instruction if bit N of port register and IO address is set. So this instruction is short, but what it does is kind of long to explain. It does a few things. It will compare the value at bit location N of the port register specified using this IO address. It will check if that bit is set or not. For example, in the earlier case, you have the button. If you press the button, you'll be reading 1 on a particular bit. So if you do this instruction, right after you get the value, you will skip the next instruction. So it's like a branch instruction, like if then else instruction. SBIC is the opposite. It will skip the next instruction if the bit is cleared. That means if that bit has a 0. Okay, so what we had earlier, let's see. Remember that we read the value from this PIMB register put into R16. We can also, instead of reading the value into a general purpose register, we can just check the value on that bit. What we do here is we are supplying the address of the PIMB register, that's 03. And then we say, let's check bit number 4, because that's the bit that we use to read the button status. So we'll check that bit. If this bit is set, that means if this PIMB4 is 1, we're going to skip the next instruction. So we're going to skip this. Okay. If it's set, we're going to skip this instruction. That means we're going to execute this instruction instead. And what this does is to set BI 0x05, 5, that is to set bit number 5 of this port B to be 1. And then we're going to jump to here, or jump down, so I'm going to skip this one. So that's the case if we have bit number 4 on this PIMB is set to 1. If it's not set to 1, if it's cleared, then we will not jump, we will not skip this next instruction. We will execute this instruction. So it will take this instruction, jump to ALT. That's going to be here. So what we're going to do is we're going to clear bit number 5 in port B register. Okay, so this is how we do if then else for this simple case.